This might seem like a simple question, but have you ever wondered how the electric motor in your child's toy or hairdryer works? With a simple flip of a switch, these devices come to life and start spinning. But how? In this video, we're diving into the basics of electricity and magnets to explain the fascinating world behind electric motors. From understanding electrical circuits to the magic of magnets, we'll uncover how motors power the everyday appliances you use. Let's get started. Basics of an electrical circuit. Let's start with the basics of an electrical circuit. Imagine you have a battery, some wires, and a device that consumes electricity, like a light bulb. When the circuit is complete and the switch is on, current flows through the wire, lighting up the bulb. But here's the catch. If there's a break in the wire, the current stops and the light bulb goes out. The path has to remain closed for the current to flow. A switch makes this easy, allowing you to open or close the circuit as needed. Now let's talk about the direction of the current. Normally, current flows in a certain direction known as the conventional current direction. If you flip the battery around, the current reverses direction, but the light bulb will still work. However, some devices like motors depend on the direction of the current. They'll behave differently if the flow is reversed. Understanding magnets. Now let's dive into magnets, a key component in electric motors. This is a magnet, and as you can see, it has two poles, the North Pole and the South Pole. Magnets are fascinating because, well, opposite poles attract while like poles repel. This is the basic principle behind magnetism. If you bring another magnet close, you'll notice that the North Pole of one magnet is drawn to the South Pole of the other. But the two North Poles will push each other away. Magnets don't have to be the traditional bar shape you see here. They can be made in all sorts of forms. For example, some magnets are flat. But the key takeaway is that magnets are always on like permanent magnets. These magnets have magnetic domains, which are tiny regions within the magnet where the magnetic fields are aligned. In permanent magnets, all of these domains point in the same direction, making the magnet constantly active. It's why we call them permanent. You can't just turn them off, unlike some other types of magnets we'll explore in a moment. Creating an electromagnet. Now let's take a look at how to create an electromagnet. Unlike permanent magnets, electromagnets are special because they can be turned on and off. To create one, we start with a metal screw. The screw itself isn't magnetic. Its magnetic domains are all pointing in random directions. However, when we wrap a wire around it and connect it to a battery, we've created a current flowing through the wire. This current causes the magnetic domains in the metal screw to align, turning it into a magnet. The cool part about electromagnets is that you can control them. If you turn off the current, the magnetism disappears. If you reverse the current by flipping the battery around, the poles of the electromagnet reverse too. North becomes south and south becomes north. This ability to control the magnetic field is why electromagnets are used in so many devices, including electric motors. Electromagnets allow us to manipulate the magnetic field for specific purposes. Unlike permanent magnets that remain constant, this versatility in creating and controlling the magnetic field is a huge advantage in motor design, allowing precise movement and performance. By controlling the direction of the current, we can achieve different mechanical outcomes, which is exactly what makes electromagnets so powerful in motors. This concept of switching the poles is a crucial part of how motors work, so keep this in mind as we continue building our understanding of electric motors. Now, let's talk about the rotating magnet concept. Now that we understand the basics of electromagnets, let's move on to the concept of a rotating magnet. Imagine we take our electromagnet and place it on a pivot so that it can rotate freely. As soon as we bring a permanent magnet close, the electromagnet will align itself so that opposite poles face each other, with the north pole of the electromagnet attracted to the south pole of the permanent magnet. But here's the exciting part. If we reverse the current flowing through the wire, the poles of the electromagnet will swap. Now, instead of attracting, the like poles will repel each other. This causes the electromagnet to rotate as it tries to align itself with the new poles. By continuing to reverse the polarity of the electromagnet, we can make it keep rotating. The ability to continuously reverse polarity is the principle that allows electric motors to produce rotational motion. It's a simple yet effective method for turning electrical energy into mechanical movement. By adding more magnets and electromagnets, we can enhance this rotation and create powerful, efficient motors. This is the foundation we'll build upon as we continue to design and optimize real-world motors. Now first, like always, be sure to hit the like button down below. It helps us out tremendously with the reach of this video. Thank you. To make the motor keep rotating smoothly, we need a way to keep the electromagnet's polarity switching automatically, without us manually flipping the battery. This is where the commutator comes in. A commutator is a ring with gaps at opposite sides that rotates with the armature, the rotating part of the motor. The commutator allows the current to switch direction without us needing to touch the wires directly. Alright, imagine the commutator as this bridge between the stationary brushes and the rotating armature. As the armature spins, the brushes, which are these spring-loaded contacts, maintain contact with the commutator. The current flows through the brushes and the commutator to the electromagnet, powering it up. But here's the magic. As the armature rotates, the commutator switches the brush's contact to the next set of commutator segments. This reversal causes the current to flow in the opposite direction through the armature, which reverses the poles of the electromagnet and keeps it rotating. This switching happens constantly, allowing the motor to keep turning. The commutator automates the task of reversing polarity, making it possible for the motor to run without interruptions. It's a simple yet ingenious design that powers many of the electric motors in our everyday appliances. Enhancing motor design. Now that we understand the basics of how a commutator works, let's enhance the motor design to make it more efficient. In our simple motor, we used a basic loop of wire in the armature. But to create a more powerful motor, we can add more loops of wire, increasing the number of windings around the armature. The more wire you have, the stronger the electromagnet becomes. This increases the motor's torque, which is the force that causes the armature to rotate. Additionally, we can improve the design by using stronger magnets like curved permanent magnets instead of simple bar magnets. These curved magnets focus the magnetic field more efficiently, allowing for a more powerful interaction with the electromagnet in the armature. This leads to smoother and faster rotation. Another improvement involves adding more windings to the armature loops themselves. More loops of wire mean that each rotation generates more magnetic force. And as a result, the motor can produce higher torque and spin faster. By using more coils and stronger magnets, we can improve the motor's performance, allowing it to power larger devices. So, electric motors aren't just for small gadgets. They're used in things like fans, electric tools, or even cars, especially when we're talking about electric vehicles. These design improvements really help create motors that are faster, more reliable, and, more energy efficient. Now let's talk a bit about motor efficiency and torque. To dive deeper into motor efficiency, we actually need to understand the concept of torque. Torque is basically the rotational force that causes the armature to spin. And, it's a critical factor in determining how powerful a motor is. The more torque a motor produces, the faster it can spin, which is super important for the devices it powers. One way to increase the torque in a motor is by increasing the strength of the electromagnet, which can be done by adding more turns of wire around the armature. More wire means a stronger magnetic field, and this results in greater rotational force. Another factor that contributes to torque is the power supply. By increasing the voltage or current supplied to the motor, we can increase the energy that flows through the electromagnet, which in turn generates more torque. More power means a stronger interaction between the armature and the permanent magnets, leading to faster rotation. In motors, the stationary parts are called the stator and the rotating parts are called the rotor. The stator provides the magnetic field while the rotor or armature carries the electromagnet and is responsible for generating the rotation. By optimizing both the stator and rotor design, we can achieve a more efficient motor that delivers higher performance with less energy consumption. And there you have it. From understanding electrical circuits to the role of electromagnets, commutators, and torque, we've seen how the basic principles of electricity and magnets come together to make electric motors work. Whether it's powering toys, hair dryers, or electric cars, motors are at the heart of many devices we use every day. If you enjoyed learning about the science behind electric motors, be sure to check out Brilliant for more hands-on learning in math and science. With their interactive approach, you can dive deeper into topics like electricity and magnetism. Thanks for watching and keep exploring.